we get that there's ninjas, right? We get that much. It's not English, but there's ninjas. Maybe you want to start out with that a little bit.
Yeah.
Like where that came from.
Well, as I said, ninjas are popular. Ninjas are good. For some reason, they were hugely popular in Serbia during the 80s when this is from a movie called How Rock and Roll Died, and it combines, some guy came up with an idea of making a band that combines ninjas, mysticism surrounding ninjas, and turbo folk, or rather folk pop music. It's a hilarious movie. I would recommend check it out, but I'm not sure it's even available somewhere or if there's a translation, but piece of local lore. So I'm Alex. I come from Serbia. I'm part of the Talos vulnerability development team. My team at Talos, at Cisco Talos, does zero-day research. We are tasked with finding vulnerabilities in commodity software. You can see some of our work at our website under vulnerability reports, or some of our open source software and some tools that we've developed at this GitHub link. So what am I going to talk about today is basically a walkthrough to this neat little vulnerability that we found in a UPnP library implementation. Some of the things that make this vulnerability interesting, and some of the things that make the exploitation itself interesting. Exploiting this vulnerability required stack smash and protection bypass, which makes it somewhat interesting as a showcase. So really quickly, I'll go and make an overview of UPnP, how the protocol works, just as a refresher. UPnP is generally designed to be run on residential networks, usually as a way and a set of protocols for network discovery, for usually doing port forwarding stuff, media streaming, and things like that. It runs on top, it's built on top of SSDP, HTTP. It uses SOAP with XML, of course, and a whole bunch of fancy words there. The usual way, the most used feature of UPnP is by applications that want to make incoming connections inside a LAN, like applications behind a NAT that want to set up port forwarding on a gateway or whatever. So it's usually mostly popular with peer-to-peer applications like torrent clients, cryptocurrencies, and stuff like that. Wherever you need to basically accept incoming connections into our local network, there would be some form of UPnP support for port forwarding, probably. How does that work? Basically, the connecting application, usually on startup, sends out a broadcast UDP packet specifying, the packet is called msearch. It just says, I'm new on this network, can you please tell me what kind of UPnP functionality do you support? It sends it on broadcast, receives replies, client parses the replies, and then chooses to which of the UPnP endpoints to connect. Briefly, in a few Wireshark screenshot, it looks like this. The first packet, the client sends out the msearch request to this, obviously, broadcast address over UDP. Next, the server replies. The reply contains one header called location header, which just has an IP address, a port, and a location of an XML file that actually contains the description of the device's capabilities. And the client then proceeds to fetch that XML and proceeds to parse it to see what it can actually do. So this is basically how the XML works. There's a bunch of information there. My colleague Martin Zeiser did some interesting research with UPnP scanning over the internet. presented at this year's PacSec conference, so if that's of your interest, you can look it up. We're not going to deal with the details of the XML. So obviously, this poses an attack surface to the client application. Client fetches the XML and starts parsing it. The parser is exposed to the external XML files. And we've come to the fun part here because most UPnP library implementations, for various reasons, come with their own XML parser implementations. They're not using libxml, they have their homegrown XML parsers. And we know, for some reason, XML is hard to parse. So on one hand, it means for developers there's less dependencies because these libraries are intended for embedded devices. You don't want to put a lot of dependencies, so they're small, complete libraries. And on the other hand, we as attackers know that this means less audited, less trusted code. So I took a look. Especially at this MiniUPNP client, which is, if not first, the second most popular UPnP implementation out there. It's a relatively small library, self-contained, and it compiles on basically everything. So what's actually using it? A couple of examples here. As I mentioned, torrent clients, almost all torrent clients are using it. Here I gave a transmission as an example. On the other hand, cryptocurrencies, all Bitcoin implementations are using MiniUPNP to do their bidding. And Tor used to, and there's a fun fact with Tor use of it. So right around the time I started looking at MiniUPNP, I took a look at what's actually using it, and Tor had this tool called Tor Firewall Helper, which does what it says in the box. It pierces through firewalls, sets up port forwarding, and it did that using MiniUPNP. When I found the vulnerability, I went back to check out the Tor how the Tor uses it, and found this message waiting for me there. They basically removed the tool and left the message that they didn't trust the underlying libraries enough to have them run on their software. This wasn't used by default, but would have been interesting either way. So they rewrote their firewall helper tool in Go and then went off from there.
Do you know which dev did it?
I honestly didn't look it up, but for some reason didn't occur to me to check. It could be interesting to see. It was a definitely good decision because they have some critical code running there. Even though it wasn't run by default, a good decision to have something like that rewritten in a manageable language. So you already see where this is all going. The vulnerability that I'm showcasing is just a vanilla buffer overflow in the XML parser, stack buffer overflow in the XML parser. It's trivially triggered by just sending the overly long XML element name. It's been patched since October the 1st last year and has this CVE. A little bit of the vulnerability itself. Here we see the parser initialization. We set up a couple of callback functions. Here we're interested in IgG start element function, which is called back whenever it starts parsing XML element names, and then the parser is invoked. Next piece of the puzzle is the IgG data structure, which is used while parsing the element names. And we can see that it has a couple of string buffers with fixed size. The MiniUPNP URL max size is limited to 256 bytes. So we have a fixed size buffer. And finally, in this function, we have an unchecked memcopy call that just copies whatever we send to it into that small buffer, which is located in the stack. This clearly results in stack buffer overflow, and we want to try and exploit this. So reaching the vulnerability is relatively straightforward. You run a fake UPnP server on your local LAN network. Some victim connects to the LAN network, fires up an application that uses MiniUPNP, sends out msearch discovery, receives a reply, starts parsing the XML, and gets owned. Not much in that way. The problem here is, with exploiting this vulnerability is, or was, that since we were trying to showcase this vulnerability by exploiting a Bitcoin client, because I thought it would be an interesting situation if I would put a fake UPnP server on a local LAN, you join the LAN, fire up your Bitcoin client, and I get access to your box without ever specifically targeting you by just virtue of network discovery. The thing is, Bitcoin folks, being a bit paranoid as they should, have built their binaries with all sorts of proactive anti-exploitation protections. One of those is obviously stack smashing protection, which kind of gets in our way. So just as a recap, a few slides about how the stack smashing protection actually works. So on this slide, we have a usual function frame on the stack. At the bottom, we have local variables, in this case, a character buffer. Then we have a stack canary. Then afterwards, we have a saved frame pointer, and finally, saved return address. Above it are function arguments. When we want to exploit a stack buffer overflow, what we want to do usually is override the saved return address. But in this case, since it's protected with stack smashing protection, we have this stack canary between the buffer and the return address. If we override the stack canary with anything else than it currently is, it can be detected and would stop the exploitation. In code, in a bit of assembly, this is how it looks like. At the left-hand side, we have the function prologue that takes a value from GS segment register at offset 14 and puts it in and saves it in a local variable here called varc. GS is actually in Linux implementations, GS segment register usually points to a thread control block, which is where the stack cookie is saved. Each time a process is restarted, a random stack cookie is generated and saved in the thread control block. Here we are copying it to a local function stack at the beginning of the function. On the left hand, I'm kind of mixing my hands because I keep turning, but on the other side, we have the function epilogue, and at the end of the function, just before the function returns, we have a check for stack smashing. Here we see the store instruction comparing the value from variable C with the original value in the thread control block. XORing them, if they're the same, the result will be 0, and we continue to return from the function. Otherwise, we know that something went wrong, and stackcheckfail function will be called. And it usually results in a message something like this. You get stack smashing detected, and your process is terminated. And you get a core dump or not, but it doesn't matter. So we get this message. What's actually happening when the stackcheckfail gets called, it in turn calls fortifyfail. So it's just a wrapper for fortifyfail. Fortifyfail in turn eventually calls lib's message, which outputs that string outside. Here we start seeing a bit of a problem because lib's message has some complicated code. It parses the environment, trying to find environment variables to know what kind of output you want. It interacts with sockets, with file descriptors, writes to the screen, obviously. The problem is that this function kicks in once you detect that the process is not to be trusted. And you're executing more code in the process that you detected is not to be trusted. I'm not obviously the first one to notice this. Adam Zabrodsky has a nice paper that goes deep into stack smashing protection internals, outlining some of these ideas about it being complex. Instead of just invoking abort the instant it detects something is wrong, it just keeps executing more code. One interesting example of that was from Dan Rosenberg, who posted this example where he did a stack smash, but instead of using it for hijacking the process control, the execution of the process, he used it as an info leak. So in this example here, we have a buffer overflow, which overflows a buffer and then overwrites the main function argument, the argv of the main function's stack frame. And then when the stack smashing protection kicks in and tries to output that message, he gets the memory leak. Because if you remember here how the libs message looks like, the argument s will be the name of your binary, which comes from argv. He overwrote that, controls the pointer, points it to something that he wants leaked. So we are going to go a step further and abuse this subvert SSP for code execution. A little bit of what's actually going on once we do stack smash, once we smash the stack with different lengths. The first run with GDB, we see the stack smashing detected, the irregular message printed out. Second time, the first one was with 200 bytes. Second time, we had 4 more bytes, and we got a different crash. And if we take a look at the call stack, we see that the values of argv are mangled. So we overwrote this part of the process memory, and we get a different type of crash. Now, to get to the next part, I need to make a little detour and get into how syscalls work on Linux and something called elf auxiliary vectors. Basically since in modern times, somewhere after the Linux kernel version 2.4, all system calls on Linux were executed using this kernel vsyscall functionality or method. Before that, the regular way to invoke system calls is by invoking an interrupt 80 hex. That wasn't particularly efficient, so now lib's standard system for doing that is by using kernel vsyscall. And here we have an example of a system call being invoked. This is a write system call wrapper. We have it set up registers as you regularly would, but instead of invoking an interrupt, it calls this function pointer that's again in GS segment registered, but this time at offset 10. As I mentioned earlier, GS points to the thread control block, and thread control block is this memory structure that holds this information on the other side. At offset 10 hex, we can see that there's a sysinfo pointer. Sysinfo pointer actually points to the kernel vsyscall function, which then proceeds to execute a system call. So there has to be a way for the loader or the kernel itself to pass the location of the kernel vsyscall function to the process itself. And that's done through the loader to the libc via elf auxiliary vectors. Elf auxiliary vectors are just an array of integers that's located somewhere up the stack. So the usual stack of the Linux process has function stacks. Up of those, you have the environment, and upwards of the environment, there are elf auxiliary vectors. Some of those vectors are AT entry, which points to the entry point of the binary, ATP PHDR, which points to the ELF headers, page size information, and of course the AT sysinfo pointer, which points to the kernel vsyscall function. So what happens is that at the process startup, after the loader is finished, then process actually starts. Some of the first code that gets executed copies the pointer from the AT sysinfo auxiliary vector into the thread control block for later use. Just a little disclaimer, this is x86 specific. The mechanism is a bit different on x86-64, but similar tricks will apply. It's obviously somewhat more different on other platforms. So where am I going with this? As I mentioned earlier, stackcheckfail function is fairly complicated, and it will eventually have to write something on the screen. It outputs that warning message, and it will do so eventually by invoking a write system call. So the idea here is that if I can somehow take control and override that kernel vsyscall function, then when the stack smashing protection kicks in and tries to write to the screen, it will try to output something to the screen, inadvertently calling write. But since I have control of the function pointer, it will jump to my code. That's not going to be so straightforward for a couple of reasons. First, if we try and make a huge buffer overflow to reach ELF auxiliary vectors on the stack to overwrite them, we would inadvertently smash all the environment, which would actually make the lib smashed code crash because it's parsing the environment. Of course, we could make sure that the environment stays sane or looks good, but then another problem is that the pointer itself is already copied into a thread control block, and thread control block will, in most cases, won't be reachable with a reasonable stack overflow. Either way, even if we have a huge overflow and it was reachable, it's way off of our current location that we would overwrite basically half the system memory and kill the process anyway. So we need another venue.
Why would you want to parse the environment in the stack fail?
They have some environment variable which you can set that would make it output a different message or log it into a certain file descriptor or something like that. So it just looks for different options which you control through the environment variable. So as I said, we need another venue of attack. Interestingly, the application that we're attacking in this case is Bitcoin Qt, which is a graphical application. It uses Qt library, which means it's a threaded application, and it's using POSIX threads for it. What's interesting about threads is that they have thread local stacks. Thread local stacks means that all of that information that's kept for the binaries for the execution of system calls, it gets copied into the thread local stack. Each thread has its own local copy. And that initialization is done somewhere while creating the thread in this allocate stack function in the POSIX thread implementation. So each thread will have its own copy of the thread control block, which we've seen earlier, which then gets referenced when executing system calls, meaning that we could maybe use this as a venue for exploitation. Also, going along our way is the fact that thread local TCB would usually be located somewhere above our current ESP relatively closely, so we can relatively easily reach it and overflow it and take control of it. So as an illustration of this, I have a small example program that has a vanilla buffer overflow in it in this fvuln function. What's a bit different from the other examples is that it's creating a thread that actually calling that instruction. So in this fvuln function, we have a string copy buffer overflow, which just smashes the stack with no problems. It's just a demonstration. And on the other hand, we have a GDB session showcasing what's actually happening when we do make the stack smashing. You can see that we run the program with a buffer of 2092 plus 4 bytes, 2092 bytes to make an overflow plus 4 bytes to write what we want. And when we run the program with this buffer, it crashes with the segmentation fault error, and we can see that it crashed with EAP being set to EA, which we set upstairs when we run the program. So we've taken control over the execution, obviously, by overwriting the thread local thread control block and its sysinfo pointer. Notice that no message from stack smashing protection is printed out because this kicked in, the process crashed while it tried to invoke the write system call to actually create output on the screen. There's one problem with this is that now that we've gained initial control over the process, our kernel vsyscall function pointer is smashed. It points to some of our code. So none of the system calls that we ourselves try to execute will work. So our shell code would break, wouldn't work. So the first thing we need to do for a successful exploit is to actually repair this function pointer, write back the original value, so we can actually execute shellcode afterwards. And another problem is that we need to use ROP gadgets to bypass a non-executable stack in this case. To solve those problems, in my exploit, I use just two gadgets, two relatively simple and useful gadgets. First one is your usual stack pivot gadgets, something that you would use to get the stack pointer pointing back to the area of your buffer, the area of memory that you control, that you know what's there. And this first gadget helpfully pops 4 registers off the stack, so we get the control over 4 registers from it for free. Second gadget is what you would call write what where gadget, which uses those previously set registers to write 4 bytes of data anywhere we want. Using these two gadgets, we repair the kernel vsyscall pointer, again enabling us to execute system calls of our own, and then just proceed to execute more code. So the actual exploit breaks down to these few steps. First, the new threads gets initialized by the application. TCB info is copied to the local thread stack. Then the overflow happens. We overwrite everything up the stack. We smash the canary because we don't care about it. We smash the return address because we don't care about it. We smash everything up the stack, past the environment, and overwrite the thread local thread control block with its sysinfo pointer pointed to our first ROP gadget. We point it to this first gadget, which sets up the stack pointer and the registers, and then jumps to the second gadget, which repairs the kernel vsyscall function pointer. Then, as ROP has already kicked in, we restore it. Then we just call mprotect to set memory protections to execute and jump to our shellcode. Not much to it there. And what would be an exploitation talk without an actual vulnerability demonstration? So I'm just going to start up a VM. and hopefully it will work. You never know with these things. Okay. Just see. My IP address gets resetted every time, and my exploit is hard-coded with an IP address, so I have to reset it. So in this screen, I run the exploit. So it listens on a network interface, listens for those broadcast packets. On another screen, I'm going to run a netcat, reverse netcat, listening for incoming connectback shells. And then, obviously, I'm going to start up the vulnerable application. So the application starts up. We get a request. The fake server sends out the reply, sends out the description XML. We don't see the application anymore, but in the reverse shell, we actually gotten code execution and gotten a shell. So that has been a quick demo. Just a small conclusion. To conclude the whole talk, what we did here, we abused SSP error reporting, which is too complicated for its own good. As I said earlier, you detected that the process is misbehaving and you keep executing more code in it. You shouldn't do that, obviously. Additionally, in case that there was some syscall executed before the function returns, we wouldn't even have to abuse the stack smashing protection to get code execution. We could just reuse the same thing. So patching the SSP not to do this complicated code output wouldn't necessarily fix this issue. And I just think that this whole this vulnerability and the way it's exploited showcases how complexities of modern process run chain, different components in the modern process run chain have unforeseen consequences which can always be abused in one way or the other. And that's basically it from me today. If you have any questions, go ahead.
So, what made the Pthreads? I mean, my understanding is that in Pthreads, the thread control forgetting TCB, right? It is way too close to the rest of the stack.
Yes.
What made them not put in a guard page?
Not sure. That would be a good idea, probably. Just the way the thread local stack is set up in that allocate stack function, it just doesn't have anything in the way of doing that.
Maybe they thought the guard page would be too much to subtract from the overall stack area.
Could be, yeah. It would take too much space.
And so, is there anything in between the top of the stack and the TCB?
I'm not sure if there are any other structures, but as I was going along, smashing stuff, trying to see what's going on, only interesting things that I saw were previous function stacks and previous function frames, and then the local TCB. So I'm not sure.
So overwriting the health ops vectors would not really help much, because by the time you need it, it's already.
I just use that detour to introduce how the kernel syscall pointer gets passed from the loader to the process.
So my question is there anything in the aux vector that does get used?
That gets reused.
So we know that there is stuff that gets used there at the relocation point.
Yes.
That was our help.
Of course.
Thing,
yeah.
Right. But after that.
I haven't looked into that, I have to admit. Thank you for the questions.
Awesome stuff.
Yeah. The full exploit, and there's a blog post on our blog explaining all the stuff there too. So if you want to look it up later, feel free to do so. Thank you.